So what I'm saying is the inverse, we know this is y, and we switched x and y here, we'd have, which is what a logarithm is. That right there. So logarithms are the inverse of exponential functions. Okay, so then it also follows the idea that log b of b to the x is x. That's a simple rule because what's your exponent rule, or excuse me, what's your log rules that make this true? Let me look at this one, log 10 of 10 to the x. Think about that one. It's the same thing, just with a number now. Why is that true by log rules from Math 30? Yeah, Tatum, math? The 10 can cancel, correct, and the exponent falls to the front, right? So in your log rules, remember, if you have something in your logarithm, let's say we don't even know the base for a second, let's just say I had x cubed. That 3, by log rules, can pop to the front. So if this pops to the front, it's x log 10 of 10. Like Tatum said, these cancel. This is 1. Because this, like if we just said, what makes that possible? Well, what's the exponent of 10 have to be 10? 1. So that's where it comes from, okay? So 10 to the 1 is 10. Okay? So long story short, this x essentially goes to the front. Log 10 of 10 is 1, so it's 1x, so it's x. Okay? Here, same exact principle, except for these cancel. And we like that quite a bit for us. Okay? So these cancel, and that gives us just x. Essentially, I can do the work for you in a second, but essentially everything just cancels and the x comes down. Hello. All right, so we're just going over the basics right now of logarithms. Forgot my notes. Okay, let's look at the next one here. Okay, so then we're looking at them versus each other in terms of the inverse. All right, so here is your regular exponential function, just regular growing, okay, up to infinity. Here's your log function. You can see that they're reflected over y equals x. Okay, again, proving that they're inverses of each other. Okay, that's all this is talking you through. One simple thing, log any base to the 1 has to be 0. Right? Any log to the 1, like of 1 has to be equal to 0. Why? Because remember, b to the 0 is 1. So anything to the 0 is 1. 10 to the 0, 20 to the 0, all that stuff. Okay, just kind of exponential truth there. Any questions on this, on the summaries? Okay. Am I remembering right that you guys have learned most of this already? Yeah. Okay. All right, so x-intercept is always 1, so that's why this is 1. Okay, because when this is 1, that's 0. So that's always going to happen right there. So in a sense, limit as x approaches 0 from the right, it's going to negative infinity. So let's look at that visually. So if we approach 0 from the right, we're going this way, it's dropping. Okay? As we approach infinity, it goes to infinity. Oops, wrong picture. So as we go this way, it's going up. Okay? This is for logs. This is just showing you the inverse. We're talking about the red line right now. Let's see how well you understand your logarithms in terms of numerically. And explain to me why, a lot of people get really, really confused, why is log 10x the smaller line, like lower? Why is log, just, Nikki, I'll let you answer. Let 90 seconds people to think about that, and then I'll let you answer. So it's got 2, 3, 5, 10. Logically, you would think, why steeper 10 would be the higher one? So why with logarithms is that not the case? So think about that, and we'll let Nikita give a shot here on his answer. And it's kind of the problem here, but. Okay, Katie, you want to explain? Essentially, that's what's going to happen. But the big thing is let's think about this for a second. 10 to the something, right? If I wrote this in exponential form, it's this, right? So 10 to something what gives me an x value. See how this is lower? Because a base of 10 is going to grow extremely fast. So we need to tailor that back by having a small number there. So essentially, my x has to be like, if this is a 2, let's just say, let's put a 2 in for x. We'll say, like right here's 1, here's 2, right? So 10 to the what equals 2? Well, 10 to the 1, I'm at 10 already. So it has to be a very small fraction. And so that's why it's flatter. Now, if I'm thinking about the number 2, like we did 2y, well, when is that? Well, that's at 1, right? 2 to the y. That's why this one is going through right there. Okay, oh, wait, did I write that wrong? 2 to the y, no, it's at the 1. Oh, 1 for the y, excuse me. Right there. Okay? That's why. Because the 10 base is growing so fast, we have to tailor it back with smaller x's in order for it to actually make sense. Okay, cool. All right, let's keep just going through these summaries here of exponentials. Sorry if I'm boring you today. All right, so this one here, find the domain of that. So what would the domain of log base 10 x minus 3 be? And we'll draw it as well here. What's the domain? Right, x greater than 3. So the rules with logs is, again, we can't have a negative in here because 10 to something power will never be negative. So we can't get a negative value. We also can't have this be 0 because, unfortunately for us, or just in general, anything to the 0 power is not 0, it's 1. So we're never going to be able to get to 0 or negative. So 3 we can't have, but everything bigger. Okay? All right, so then that means that we're going to have an asymptote at 3 because we can't do that. So what essentially happens is that graph we just had, because there was no movement, we just essentially move that thing over here to 3, and we're having the same type of picture. And that's going to go through, it's going to go like this. That's essentially what the graph's going to look like. So the reason being is if you plug 4 in, 4 minus 3 is 1, so we know that value is 0. That's why it's on the 0 for the y. Okay, because this is y, right? So let's write it like this, and then let's write it like this so we can see what we're talking about here. When I put 4 in here, 4 minus 3 is 1. How do I get a 1 out of this? That's 0. So that's why it's there, 4, 0. Okay. Approaching 3 from the left, it's going to negative infinity, and approaching, going to infinity, it's going to infinity with the y. Okay? Okay. All right, now we're going to switch to natural logs. So the only thing with natural logs is we just change the base to being a base of e, so ln. Okay, log base e is ln in your calculator. Ln stands for the natural logarithm. Okay, it's right here for you. We're all familiar with that. Okay. Again, here's what e to the x looks like. Remember, e is a number like pi. Is it 1.7 or 2.7? Forget what the value is. If you hit e, enter in your calculator, it's a specific number. So 2.7. Okay, I always forget for some reason. Okay, and then this is the inverse to ln x. Okay. Any questions on natural logs? Nothing really to ask, I guess, if they're natural. All right. Okay, so what they're saying is we put b for e, so the base is now changed to e. That's all we're doing. Ln of x of y, e to the y equals x. Okay, because log base of e, right? So be e to the y equals x. That's what they're just showing you there. So then here, just like we did before, ln e to the x is equivalent to x. The same reason, right? Because it's log e base e. So we drop the x in front. Ln of e is 1. Ln of e is 1 because ln stands for log base e. Okay? Conversely, which is going to be for all of our logarithms, it's going to happen, ln of 1 is 0. The only way we're going to get 1 is we have a 0 power. That's the only way we're going to get it. Okay, so it's the same rules as we just talked about with logs. It's just talking about the base of an e now. Okay, same thing here. These will cancel, and you get x. All right. We just got a few examples here, and then we'll be done. And then, like I said, maybe we can just kind of summarize tomorrow's stuff. We'll see. We'll take a look. All right. Solve for x and ln of x. There's two ways you can do it. There's one, right? Base to the exponent equals this. E to the 8 equals x. That's a value. E is a number, just like pi. Okay? The other way you can do it, which kind of goes along with the other proof we've done, is that you could do this to both sides. So essentially, you're changing it both sides to have a base of e and putting these things as exponents. This cancels. So you have x equals e to the 8. That's the other way you can do it in terms of log solving. Okay, both are fine. Yeah. I put the number. I guess I just the number. I didn't put the number. No, that's fine.
That's good.
Yeah. Well, I mean, 2.7 to the 8 is going to be pretty big. We can leave it like that. Okay. Example 3. Solve the equation e to the 3 minus 2x equals 4. Why don't you try that for a second? See if you remember the skills it takes to get that 3 minus 2x down. That's the key. We're trying to get this down. That's why logarithms help us. Go ahead and try that. Okay, so solve this equation. So what you want to do here is you want to ln both sides to start. That's the strategy you want to use because ln of e we like because ln of e is 1. And so if I go ln e 3 minus 2x equals ln 4, this is a value. Okay, so we're okay. We bring this down by log rules. And we're happy now because this essentially is nothing. So now we have 3 minus 2x equals ln of 4. So we're going to minus the 3. So you don't get confused there. And then we're going to divide by negative 2. I'll distribute that, so I'm going to flip these. That's what x is equivalent to. 3 minus ln of 4 over 2. I just flipped them just so I could write, because this negative made that a positive, so I put positive 3. This negative made that a negative, so I just rearranged them. You would be wrong if you didn't. Okay.
Is it the same as doing like just changing it to like the ln form, like without putting an ln to both sides? Like, because you could just make it like ln to the 4 equals 3 minus 2x, right? Just like right away, right? You just do that, like how you know how it's like
Yeah.
to the y equals x, so you just like flip it back to that, or?
Yeah, I think that's fine.
Okay.
Yeah. Okay. Okay. So this here. So sketch the graphs of the following functions. We're looking at what negative ln looks like and ln of negative x. So when you do the negative here, which we understand by our rules from the very beginning of the year with reflections, what that does is it's giving you a negative output, so it's flipping it over the x-axis. Okay, so it's flipping your y, right? Here, it's flipping the x, so it's going over the y-axis. That's a difference in the image there. Okay, instead of having you guys sketch them as, or me trying to sketch them neatly, I put them on there. Okay, so again, it's that same form that we've been working with the whole year. That's my original. I'm changing my original to the opposite of it. If I do that, now I'm flipping over the x. Okay, this one here, I flipped the x, therefore I'm over my y-axis. Okay. Okay, next thing I'm just going to talk about kind of how the domain can change, but in terms of the limits, we won't need that for right now. It's just talking about how it falls off. Okay, so find the domain of this one. So what's the domain of that one? I want you to focus on that, and then I'll just kind of tell you what this is explaining. So what's the domain of that? I'll give you a hint. Between -2 and 2. Okay, because 2 and -2 both make us have 0. And if I have anything on the outside of those, I am bigger than 4, which makes it a negative. Okay, does that make sense? 4 minus x squared. So if I put 2 here, that's a 4. If I put -2, that's a 4. So that's kind of my breakpoints. Do I want outside or inside? Well, I want inside because if I go 5, 4 minus 5 squared is -21. We don't want negatives in there. So that's your domain. This, essentially, the image looks like this. It's a semicircle. So then what it says is, we know this with ln already. Like our ln, let's go back here real quick. Let's look at this guy for a second. See this ln? As we approach 0 from the right, so from the right, what's it doing? -infinity. Okay? As we approach 0, or excuse me, if we approach infinity, so as we go this way, it's approaching infinity. So that's all this is. Not really need to skip it, but that's all it's asking. So then we'll just kind of do number 6 here. It asks us on the next one, it says same problem, 2 from the left. So this picture, if I'm going from 2 from the left, what's it going to? Because these are essentially asymptotes, right? It doesn't stop.
Oh.
It's just kind of bounded. So -infinity. Okay, that's all 6 is asking for. Okay, quick summary of your rules here. We just did this if you weren't paying attention. Just talked about this image from 2 from the left, it drops to -infinity. So the answer for this is -infinity. ln x of y with log rules is ln of x plus ln y as long as they're real numbers. ln of x over y is ln x minus ln y, and then this is the power rule. You can drop the r in front, r ln of x. Okay, as long as they meet those requirements. We're almost done here. Okay, so a little practice of that. We're going to write this as a single logarithm. So we're going to write this as a single logarithm. So push the 1/2 up. Push the 4 up. Keep that as it is. Okay, so essentially, negatives in addition tells you top or bottom, really, because this means division, this means multiplication. So if I multiply to this, it's just going to be on the top. Okay, so all it's going to be is this. ln x to the 1/2, we'll put it at times, or excuse me, no, plus. I'll put it as a plus for a second. No, I won't. No, I won't. I'm just going to write multiply, just like that. That's essentially the answer with 1 ln. And really, this whole thing is, let's slide this over just a bit. It's really like that, really. Multiply those guys at the top because they're positive ln's. Divide the y4 because it's negative.
Why do you minus the x squared plus 1 instead of adding?
It's a times. This is like multiply. Okay, so you can multiply them too if you'd like and just like combine like terms. Like this would be x to the 2.5, so 5/2, and this would be x to the 1/2, but I left it like that. Okay, real quick now, change the base, which you guys have done quite a bit. I remember the 30 when I was doing tutoring for that. So change the base is quite simple. It is normally a regular log has a normal base of 10, but if you're dealing with not normal bases, so whatever it is, log of the x there with a base 10 over a log of the base 10 with the a there. So a quick one I can do, if I was trying to do log 5, 6, I would do log 6 in your calculator, whether that's a 10, over log 5. That's all you have to do to change the base. It's a change of base formula. This is just telling you they're essentially inversed. So log a of b is the same thing as 1 over log b of a. All right, just got one last example here. So evaluate log 8.5 to 6 decimal places. So you'll just do that in your calculator. Do that in your calculator, you should get that right there. And again, the general rule is if you don't have a base, it's assumed to be a 10, just like a square root's assumed to be a 2. Okay, that's it.